Max Planck's journey into the realm of quantum theory is one of the most captivating tales in the history of science. It begins at the turn of the 20th century, when the traditional laws of classical physics, based largely on the works of Isaac Newton, could not explain certain phenomena that were becoming increasingly important. Planck's deep dive into the intricacies of physics began not with an intention to revolutionize the very fabric of science, but rather as an attempt to solve a pressing, very real issue in physics: the nature of blackbody radiation. Blackbody radiation was a mystery that had confounded scientists for decades. This term refers to the emission of electromagnetic radiation by a body that absorbs all incident radiation, regardless of frequency or angle of incidence. Planck's own role in this puzzle would be nothing short of groundbreaking, as his work laid the foundation for what would become quantum mechanics, a theory that would later reshape the entire scientific worldview. At the time, physicists were dealing with a critical problem known as the ultraviolet catastrophe. This phenomenon arose in classical physics from a prediction made by the laws of thermodynamics and electromagnetism, specifically from Rayleigh and Jean's law, which described the intensity of radiation emitted by a blackbody as a function of temperature and wavelength. The problem was that this law, derived from classical physics, suggested that as the wavelength of radiation approached the ultraviolet range, the intensity of radiation would approach infinity. In simple terms, it meant that a perfect blackbody would radiate an infinite amount of energy at short wavelengths, something that was not only impossible, but was also not supported by experimental observations. For years, this discrepancy between theory and experiment had baffled scientists. Classical physics simply couldn't account for the observed emission of light from heated bodies, especially at high frequencies, where the intensity should not have been infinite. This was a key moment in the development of physics, as the inadequacies of the classical models began to surface, and it became clear that something was missing in the equation. Planck, like many other physicists of his time, sought to resolve this issue. However, his approach was different. He didn't set out to overthrow classical physics, but to build upon it. At the heart of his work was the understanding that classical physics was incomplete. He believed that the classical view of continuous energy distribution was insufficient to explain certain experimental results, particularly those related to blackbody radiation. Planck's brilliance lay in his ability to see that energy might not be distributed continuously, as classical physics suggested, but instead in discrete packets or quanta. This idea was not only a challenge to the prevailing wisdom of the time, but also a bold departure from the way physics had understood energy transfer. In 1900, while studying the problem of blackbody radiation, Planck formulated a new hypothesis. He proposed that energy could be emitted or absorbed only in specific amounts, or quanta, rather than in a continuous stream. This was the genesis of quantum theory, a theory that would later be expanded by physicists like Albert Einstein, Niels Bohr, and Werner Heisenberg. Planck's breakthrough came when he introduced the concept of the Planck constant, a fundamental physical constant that characterizes the size of these energy quanta. He argued that the energy of these quanta was proportional to the frequency of the radiation, a relationship captured by the formula E equals h nu, where E is the energy of the quantum, is the Planck constant, and nu, the Greek letter nu, is the frequency of the radiation. This was a radical departure from the classical understanding of energy as being continuous. For Planck, energy existed in discrete units, and the only way to explain blackbody radiation correctly was to consider these quanta. Planck's hypothesis was initially met with resistance. After all, the idea that energy could be quantized seemed counterintuitive to many physicists who believed that energy was a continuous quantity. It was, however, the only explanation that matched the experimental data. By introducing the concept of quantization of energy, Planck was able to explain the observed spectrum of blackbody radiation, something that had eluded scientists for decades. This was the first instance where quantum concepts were applied in a practical way to solve a physical problem. Despite its revolutionary nature, Planck himself didn't fully grasp the broader implications of his discovery. He was simply trying to solve a specific problem in physics, without realizing that he had just opened the door to an entirely new field of study. The introduction of the quantization of energy, while monumental, was viewed by Planck as a temporary mathematical tool to make sense of the blackbody radiation curve. He did not immediately envision the radical shift in understanding of the physical world that this concept would eventually lead to. The significance of Planck's work became clearer only as the years went on. As Planck's quantum theory gained traction, it sparked a new wave of ideas and inspired other physicists to look for quantum explanations for other phenomena. Albert Einstein, for instance, would use Planck's concept of quanta to explain the photoelectric effect, showing that light could behave as discrete packets of energy, which led to his famous work on the nature of light and the development of quantum mechanics. In the early days, however, Planck's ideas were not immediately recognized for their far-reaching implications. Planck himself was hesitant to embrace the full consequences of his theory. He viewed the idea of quantization as a mathematical tool, not a physical reality. It wasn't until later, especially with the advent of the work of Einstein and others, that the idea of quantization would be fully embraced and recognized as a fundamental principle of nature. Planck's introduction of the Planck constant, h, was equally crucial. It marked the first appearance of a universal constant that would play a central role in the development of quantum mechanics. The Planck constant would later appear in numerous equations and become one of the cornerstones of quantum theory, helping to characterize the behavior of particles at microscopic scales. It set the scale for the quantization of energy and provided the framework for understanding the behavior of atoms and subatomic particles, which classical physics could not explain. Max Planck's theory did not just offer a solution to a specific problem. It opened up a whole new realm of physics that defied the classical laws of mechanics. It was an idea that was initially met with skepticism, but would ultimately reshape the entire landscape of science. His work was foundational to the development of quantum mechanics, a theory that would go on to explain everything from the behavior of electrons in atoms to the mysterious workings of the universe at its most fundamental level. The development of quantum theory would eventually lead to the creation of technologies that would change the world, from semiconductors to lasers and computers. What makes Planck's contribution so remarkable is that it came at a time when classical physics was at its peak. The successes of Newtonian mechanics, thermodynamics, and electromagnetism had led many scientists to believe that the major laws of nature were already understood. Yet, Planck's work would show that there was much more to discover, that the universe operated at levels beyond the reach of classical concepts. By introducing the idea that energy was quantized, Planck shattered the notion that physics was fully understood. His work would ignite a scientific revolution that continues to shape our understanding of the universe today. Max Planck's discovery of the quantum was not just an academic achievement, but a fundamental shift in how we view the world around us. It bridged the gap between the classical and modern views of physics, showing that the universe operates on scales and in ways that we are still working to fully comprehend. His journey from classical physics to quantum theory is a testament to the power of curiosity, the willingness to question established knowledge, and the profound impact that one mind can have on the world of science. It was not just about solving a specific problem, but about opening up a whole new way of thinking that would influence the course of physics for generations to come. Max Planck's journey, though initially rooted in resolving a specific scientific problem, sparked an intellectual revolution that changed the entire course of physics. The acceptance of his quantum theory was gradual, and its implications unfolded slowly, as Planck's ideas would eventually evolve from a mathematical tool to a fundamental cornerstone of modern physics. Despite the radical nature of his hypothesis, which clashed with the established views of classical physics, Planck's work opened the door to an entirely new way of understanding the physical universe. To truly appreciate the significance of Planck's work, it's crucial to understand the intellectual climate of his time. The late 19th and early 20th centuries were a period of immense scientific progress, but many questions remained unanswered, especially in the field of thermodynamics and radiation. Classical physics, governed by the laws of Newton and Maxwell, had explained a great deal about the nature of the macroscopic world, but it was starting to show cracks when applied to the atomic and subatomic levels. Classical laws could not account for the behavior of radiation emitted by heated objects, and particularly, they failed to explain the behavior of light at very short wavelengths, such as ultraviolet light. The ultraviolet catastrophe, a term coined to describe the discrepancy between theory and experiment, was one of the most pressing issues in late 19th century physics. Classical physics, as explained by Rayleigh and Jeans, predicted that an ideal black body, a perfect emitter and absorber of radiation, would radiate infinite energy at short wavelengths, a conclusion that did not match the experimental results. Instead of infinite radiation at ultraviolet wavelengths, experiments showed that the intensity of radiation decreased as the wavelength shortened. Planck's task, therefore, was to find a way to explain this discrepancy. His approach was unconventional for the time. Rather than simply tweaking existing models of classical physics, Planck introduced the idea that energy, rather than being a continuous flow, was emitted or absorbed in discrete quantities or quanta. This was a departure from centuries of thinking in physics, where energy had been seen as a smooth, continuous substance. Planck's quantum hypothesis was purely mathematical at first. He did not think of it as a new theory of nature, but rather as a tool to make sense of the experimental data. However, the implications of his hypothesis were far-reaching. It marked the first instance in history where energy was considered in discrete packets, laying the foundation for the later development of quantum mechanics. The introduction of the Planck constant, h, was another significant aspect of his theory. The constant, which related the energy of a quantum to its frequency, was initially just a constant that Planck introduced in his formula for blackbody radiation. The formula E equals h nu, where E is the energy of the quantum, h is Planck's constant, and nu, the Greek letter nu, is the frequency of radiation, would later become one of the most important relationships in quantum theory. But at the time, Planck didn't realize that this constant would play such a central role in the future development of physics. It was simply a mathematical tool to help explain the energy distribution in blackbody radiation. What made Planck's constant so significant was not just its ability to solve a specific problem, but its fundamental nature. It was the first physical constant that introduced a discrete structure into the continuous world of classical physics. This constant became central to quantum mechanics, where it governed the behavior of particles and energy at the atomic and subatomic levels. Later developments in quantum theory, such as wave-particle duality, Heisenberg's uncertainty principle, and Schrödinger's wave equation, all built upon this quantization of energy that Planck had first introduced. Despite the groundbreaking nature of Planck's discovery, he did not initially see the full scope of its implications. Planck's quantum theory was a resolution to a problem in thermodynamics, not an invitation to rethink the entire framework of physics. In fact, Planck himself was reluctant to accept the broader consequences of his work. He regarded the quantum hypothesis as a mathematical convenience, a temporary solution to an immediate problem. He was hesitant to fully embrace the idea that energy was fundamentally quantized, and he even resisted the idea that it had any deeper physical reality. For Planck, it was a necessary tool to match theory with experimental data, but he did not view it as an essential principle of nature. It wasn't until the work of other physicists that the full significance of Planck's theory began to be understood. Albert Einstein, in 1905, applied Planck's concept of energy quanta to the photoelectric effect, where light shone on a metal surface and caused the emission of electrons. Classical physics couldn't explain this phenomenon, but Einstein showed that the energy of light must be quantized, behaving like particles or photons. This was the first real physical manifestation of Planck's theory, and Einstein's work, for which he won the Nobel Prize, provided the empirical validation that Planck's ideas had real physical consequences. Meanwhile, Niels Bohr, building on Planck's work, developed his model of the atom, introducing quantized orbits for electrons in the hydrogen atom. Bohr's model was a direct application of Planck's quantum theory, where the energy levels of the electron in an atom were quantized, explaining the discrete spectral lines observed in atomic emission spectra. This was a significant step toward the development of modern atomic theory. In the years following Planck's initial hypothesis, other physicists, including Heisenberg, Schrödinger, and Dirac, would extend and refine the quantum theory. Heisenberg's uncertainty principle, Schrödinger's wave mechanics, and Dirac's quantum field theory all relied on the fundamental idea of energy quantization that Planck had introduced. In essence, Planck had laid the groundwork for a new scientific paradigm that would replace classical mechanics in explaining the behavior of matter and energy at microscopic scales. Max Planck's contributions didn't just lead to the birth of quantum mechanics. They also gave rise to an entirely new way of thinking about the universe. His work was a bridge between the deterministic worldview of classical physics and the probabilistic nature of quantum mechanics. The shift from continuous to discrete, from the deterministic laws of classical physics to the uncertainty and probabilistic models of quantum theory, represented a fundamental transformation in human understanding. Quantum mechanics opened up new areas of study in physics, leading to the development of fields such as quantum chemistry, quantum computing, and quantum information theory. It provided the theoretical underpinnings for technologies that have transformed the modern world, from semiconductors and lasers to medical imaging devices and nuclear energy. The Planck constant, once an obscure mathematical tool to solve a specific problem, became a central fixture in the scientific and technological advances of the 20th century and beyond. In summary, Max Planck's work on blackbody radiation marked the birth of quantum theory, a discovery that would have profound implications for the entire scientific community. His introduction of quantized energy and the Planck constant revolutionized the way physicists viewed the world, leading to the development of quantum mechanics and reshaping our understanding of the physical universe. Though Planck himself did not foresee the full impact of his work, his contributions laid the foundation for much of modern physics and opened the door to a deeper exploration of the microscopic world. His legacy is one of the most significant in the history of science, as his quantum theory continues to influence the way we understand matter, energy, and the fundamental laws of nature. Max Planck's introduction of the idea that energy is quantized, which he proposed in 1900, would prove to be one of the most profound shifts in the history of physics. This concept did not emerge from nowhere. Rather, it stemmed from Planck's efforts to solve one of the most pressing problems in physics at the time: the mystery of blackbody radiation. Classical physics, dominated by Newtonian mechanics and the laws of thermodynamics, had long worked well in explaining the behavior of macroscopic systems. However, as scientists delved deeper into the realm of the microscopic, they found that classical models could not fully account for certain phenomena, particularly at the atomic and subatomic levels. The failure of classical physics to explain blackbody radiation was one of these critical gaps, and Max Planck's approach to resolving this problem led him to the groundbreaking insight that energy is not continuous, but rather is quantized. The problem of blackbody radiation had been a long-standing issue in physics. Classical theory, based on the laws of electromagnetism and thermodynamics, predicted that the radiation emitted by a blackbody, a theoretical object that absorbs all incident radiation and emits radiation across a spectrum would increase infinitely at shorter wavelengths, a phenomenon known as the ultraviolet catastrophe. This prediction, however, did not match experimental data. In reality, blackbody radiation at short wavelengths did not increase infinitely, but instead followed a curve that had been experimentally observed. The discrepancy between theory and experiment was baffling to scientists and pointed to the fact that classical physics was incomplete when it came to explaining the behavior of radiation at microscopic scales. Planck, a German physicist, was tasked with solving this problem. He approached the issue with a fresh perspective. Planck did not simply try to tweak existing models. Rather, he questioned the very foundations of classical theory. He introduced a revolutionary idea: the concept that energy is emitted or absorbed in discrete amounts, or quanta, rather than being transferred continuously, as was previously believed. This was a radical departure from the classical understanding of energy and would lay the foundation for the quantum revolution in physics. In 1900, Planck proposed that energy is quantized in such a way that it can only be emitted or absorbed in specific, fixed amounts. He introduced a constant, now known as the Planck constant, denoted by Isabaktudenproj, h, to describe the size of these energy quanta. The energy of each quantum was proportional to the frequency of the radiation, a relationship captured by the formula Riden Isabaktudenproj. Isabaktudenproj. E equals HNIU, where Riden, E, is the energy of the quantum, Isabaktudenproj, H is the Planck constant, and Isabaktudenproj, NIU, the Greek letter nu, represents the frequency of the radiation. This formula was the key to resolving the discrepancy between classical predictions and experimental observations of blackbody radiation. At first, Planck himself did not fully grasp the revolutionary nature of his discovery. He viewed his quantization of energy as a mathematical trick, a necessary hypothesis to resolve the issue of blackbody radiation. Planck was not the first physicist to question the continuous nature of energy, but he was the first to provide a mathematical framework that not only explained the blackbody radiation curve, but also fit experimental data. His work opened the door to an entirely new way of thinking about energy and its interaction with matter. However, Planck's acceptance of energy quantization as a physical reality was tentative at first. He thought of it as a temporary solution rather than a fundamental truth of nature. The concept of energy quanta was difficult for many physicists to accept at the time. Classical physics had been the dominant paradigm for centuries, and the idea that energy could only exist in discrete packets was completely counterintuitive. Nevertheless, Planck's theory was the only one that could explain the observed spectrum of radiation, and over time, it gained traction in the scientific community. Planck's work not only solved the problem of blackbody radiation, but also opened up a new realm of scientific inquiry that would eventually lead to the birth of quantum mechanics. The introduction of quantized energy fundamentally altered the way scientists understood the microscopic world. While classical physics was concerned with macroscopic phenomena such as the motion of planets or the behavior of gases, Planck's theory suggested that at the atomic and subatomic levels, the laws of nature were governed by entirely different principles. This was the beginning of a profound shift in our understanding of the universe. Classical mechanics had been remarkably successful in explaining the behavior of everyday objects, but at the atomic scale, it simply did not apply. Planck's work demonstrated that energy behaved differently at this scale, and it marked the dawn of the quantum era. While Planck's ideas were groundbreaking, they were not immediately embraced by the scientific community. Many physicists struggled to accept the idea of quantized energy, and it was not until Albert Einstein's work on the photoelectric effect in 1905 that Planck's theory gained broader recognition. Einstein extended Planck's concept of energy quanta to explain the photoelectric effect, where light striking a metal surface caused the emission of electrons. Classical wave theory could not explain this phenomenon, but Einstein showed that light itself could be thought of as discrete packets of energy, or photons, just like Planck had suggested for blackbody radiation. Einstein's work was instrumental in demonstrating the physical reality of Planck's quantization of energy, and it provided the experimental evidence that the world of physics was changing in a fundamental way. The notion of energy quantization would soon become a central tenet of quantum mechanics. In the years following Planck's initial discovery, scientists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger would develop quantum mechanics into a full-fledged theory, extending Planck's ideas into new realms of understanding. Bohr, for example, used Planck's concept of quantized energy levels to explain the discrete spectral lines of hydrogen, while Heisenberg's uncertainty principle and Schrödinger's wave mechanics further built upon Planck's early work. Planck's contribution was thus not just a solution to a specific problem, it was the foundation upon which the entire quantum theory was built. One of the most remarkable aspects of Planck's theory is that it bridged the gap between the classical and modern worlds of physics. Classical physics had been built on the assumption of continuous processes, but Planck's work demonstrated that at the microscopic level, nature operated in discrete steps. This realization shattered the deterministic worldview of classical mechanics and paved the way for a new understanding of the universe, one that was inherently probabilistic and uncertain. The impact of Planck's work extended far beyond the confines of theoretical physics. The advent of quantum mechanics revolutionized many fields of science and technology. Quantum theory provided the framework for understanding the behavior of atoms, molecules, and subatomic particles, and it formed the basis for the development of technologies like lasers, semiconductors, and quantum computers. The birth of quantum mechanics also influenced other fields of science, including chemistry, where it helped explain the nature of chemical bonds and reactions. Planck's theory, though initially a response to a specific problem in blackbody radiation, set the stage for a new era of scientific discovery. Max Planck's contribution to the development of quantum theory is one of the most significant achievements in the history of science. By introducing the idea of quantized energy, he not only solved a critical problem in physics, but also reshaped our understanding of the universe. His work set the stage for the development of quantum mechanics, a theory that would later revolutionize physics and lead to groundbreaking discoveries and technological advancements. Planck's quantum theory provided a new lens through which to view the atomic and subatomic worlds, and it continues to shape the direction of scientific research to this day. To understand the magnitude of Planck's achievement, it is important to recognize the context in which he was working. The late 19th century was a time of remarkable scientific progress, but there were still many unanswered questions. Classical physics had reached its peak, but it was clear that there were gaps in its ability to explain certain phenomena, particularly at the atomic and molecular levels. Planck's insight into the quantization of energy provided the key to unlocking these mysteries, and it set the stage for a new era in physics. His work marked the end of an era dominated by classical mechanics and the beginning of the quantum revolution that would redefine our understanding of the universe. Max Planck's discovery of quantized energy was not just a mathematical solution to a scientific problem. It was a paradigm shift that would change the course of physics. His work opened the door to the quantum world, a world that is fundamentally different from the macroscopic world that classical physics had described. Today, the Planck constant, h, is a fundamental constant in physics, and quantum mechanics remains one of the most successful and influential theories in all of science. Planck's contribution, though initially met with skepticism, has had a lasting impact, and his name is forever associated with the birth of quantum theory. The acceptance and expansion of Max Planck's theory laid the groundwork for what would become the full development of quantum mechanics in the early 20th century. Though Planck himself had introduced the quantization of energy as a mathematical construct to resolve the problem of blackbody radiation, it was not until the work of others, notably Albert Einstein, Niels Bohr, and Werner Heisenberg, that quantum theory blossomed into a comprehensive framework. The revolutionary nature of Planck's quantum theory was not immediately recognized for its broader implications. However, as physicists continued to probe deeper into the microscopic world, Planck's initial work on energy quantization became the bedrock for the entire field of quantum mechanics. In 1905, a few years after Planck had proposed the idea of quantized energy, Albert Einstein extended Planck's concept to explain the photoelectric effect. Classical wave theory had failed to account for the phenomenon where light striking a metal surface caused the emission of electrons. Einstein, building on Planck's ideas, suggested that light was composed of discrete packets of energy, which he called quanta, or photons. Einstein's explanation of the photoelectric effect demonstrated that light could behave both as a wave and as a particle, solidifying the concept of energy quanta as a fundamental physical reality. This work earned Einstein the Nobel Prize in Physics in 1921, further cementing the idea that Planck's theory was not just a mathematical tool, but an essential concept in understanding the behavior of light and radiation. Einstein's contribution was critical because it provided empirical evidence for the quantization of energy. Planck's original hypothesis had been mathematical and theoretical with the purpose of explaining blackbody radiation. However, it was Einstein's work on the photoelectric effect that showed the real-world relevance of quantization. Einstein's insights into the nature of light as both a wave and a particle were part of the larger wave-particle duality that would become one of the central ideas in quantum mechanics. Wave-particle duality, where particles like light or electrons exhibit both wave-like and particle-like properties, would later be formalized and explored in detail by other physicists like Niels Bohr and Louis de Broglie. Niels Bohr, another key figure in the development of quantum theory, took Planck's ideas about quantized energy levels and applied them to the atom. In 1913, Bohr introduced his model of the hydrogen atom, where electrons could only occupy specific, quantized energy levels. This was a groundbreaking departure from classical physics, which had assumed that electrons could move freely within an atom, occupying any energy level. Bohr's model explained the discrete lines observed in the atomic spectra of hydrogen, something that had been a mystery for years. By incorporating Planck's concept of quantized energy, Bohr was able to show that electrons in an atom could only gain or lose energy in specific amounts corresponding to the difference between the quantized energy levels. This model, though later refined by quantum mechanics, was a major leap forward in understanding atomic structure and the behavior of electrons. While Bohr's model was instrumental in explaining atomic spectra, it was still based on classical concepts, and it was clear that something more fundamental was needed to describe the full behavior of electrons and other subatomic particles. The next major step in the development of quantum mechanics came with the work of Werner Heisenberg and his uncertainty principle, formulated in 1927. Heisenberg's uncertainty principle stated that there is a fundamental limit to how precisely we can simultaneously know certain pairs of properties of a particle, such as its position and momentum. This principle was a direct consequence of the quantum nature of matter, where particles did not have precise, deterministic trajectories, as classical mechanics had assumed, but rather existed in a state of probability. Heisenberg's uncertainty principle further shattered the classical worldview by introducing a fundamental indeterminacy in the behavior of particles. In classical physics, it was assumed that if one knew the position and velocity of a particle, one could predict its future behavior with certainty. However, Heisenberg showed that at the quantum level, this was not possible. The more precisely one measured the position of a particle, the less precisely one could know its momentum, and vice versa. This uncertainty was not a limitation of experimental techniques but a fundamental feature of nature. It demonstrated that the universe at its most basic level is probabilistic rather than deterministic. This idea would be explored further by Schrödinger and others, leading to the development of wave mechanics and the formalization of quantum theory. Wave mechanics, introduced by Erwin Schrödinger in 1926, provided a mathematical framework for understanding the behavior of particles at the quantum level. Schrödinger proposed that particles like electrons could be described by wave functions, mathematical functions that gave the probability of finding a particle in a particular location. This idea of describing particles as waves rather than as discrete objects was another key development in quantum mechanics. Schrödinger's wave equation, which describes how the wave function of a system evolves over time, became one of the most fundamental equations in physics. It was a direct consequence of Planck's quantization of energy, as it relied on the idea that energy levels are discrete and that particles have wave-like properties. One of the most striking aspects of quantum mechanics is its departure from the deterministic worldview of classical physics. In classical mechanics, the behavior of a system can be predicted with certainty if the initial conditions are known. In quantum mechanics, however, the future behavior of a particle is governed by probabilities. The wave function of a particle provides the probability distribution for where the particle might be found, but it does not provide a definite answer. This probabilistic nature of quantum mechanics was a radical departure from the certainty and determinism of classical physics, and was one of the reasons why quantum mechanics was initially met with resistance. Many physicists, including Albert Einstein, struggled with the idea of a probabilistic universe, famously stating, "God does not play dice with the universe." Despite Einstein's reservations, quantum mechanics has since become one of the most successful theories in the history of science. It has been confirmed by countless experiments and has led to a range of technological advancements, from the development of semiconductors and lasers to the advent of quantum computing. The foundational ideas introduced by Planck, Einstein, Bohr, Heisenberg, and Schrödinger have been instrumental in shaping the modern world. Max Planck's theory of quantized energy was the catalyst that sparked the quantum revolution. His work provided the framework for the later development of quantum mechanics, which fundamentally changed our understanding of the physical world. Planck's concept of discrete energy levels and the introduction of the Planck constant, h, not only solved a critical problem in blackbody radiation, but also opened the door to a new way of thinking about the universe. The development of quantum theory, through the work of physicists like Einstein, Bohr, Heisenberg, and Schrödinger, would go on to revolutionize science and technology, leading to advancements that have transformed our world in ways Planck could never have imagined. Max Planck's legacy lies not just in the specific problem he solved with blackbody radiation, but in the radical shift he brought about in how we perceive the universe. His introduction of energy quanta marked the beginning of a new era in physics, one where the deterministic laws of classical physics gave way to the probabilistic, uncertain nature of quantum mechanics. His ideas paved the way for discoveries that continue to influence scientific thought and technological development today. Max Planck's introduction of the Planck constant and the quantization of energy marked a pivotal moment in the history of science. His work in 1900, aimed at solving the problem of blackbody radiation, would not only provide a solution to a long-standing issue, but also lay the foundation for the creation of quantum mechanics. The problem of blackbody radiation, which had eluded physicists for decades, was based on the failure of classical physics to explain the observed behavior of radiation emitted by heated bodies, particularly at high frequencies or short wavelengths. Classical theories predicted that the intensity of radiation would increase infinitely as the wavelength became shorter, a phenomenon known as the ultraviolet catastrophe. However, experiments did not support this prediction, showing instead that radiation intensity dropped at short wavelengths, leading to a mismatch between theory and experiment. Planck was tasked with resolving this issue, and his approach to the problem was revolutionary. Unlike other physicists of his time, who attempted to modify existing classical theories, Planck took a step further by proposing that energy could only be emitted or absorbed in discrete packets, which he called quanta. This idea was a stark departure from the classical view that energy was continuous. Planck's introduction of this concept of quantization would reshape the way scientists viewed energy and matter, marking the beginning of a new era in physics. His formulation of the Planck constant, denoted by h, was the mathematical expression that linked energy to the frequency of radiation. The equation E equals h and nu encapsulated the relationship between the energy of a quantum and the frequency of radiation, where nu is the frequency and h is the Planck constant. This seemingly simple equation would prove to be one of the most important in the history of physics. When Planck introduced the concept of energy quanta, he was not yet aware of the full implications of his discovery. At first, he regarded the idea of quantization as a mathematical device rather than a reflection of physical reality. He sought to solve the problem of blackbody radiation, not to establish a new physical principle. However, as more experiments and theoretical advancements followed, the quantization of energy would reveal itself to be a fundamental characteristic of nature, one that transcended the problem Planck had initially set out to solve. It became clear that energy, at the atomic and subatomic level, did not behave as a continuous quantity, as had been previously assumed, but rather in discrete units, or quanta. This was the first step toward a completely new way of understanding the microscopic world, one that would later lead to the development of quantum mechanics. The introduction of the Planck constant marked the beginning of a shift in the scientific understanding of energy and matter. Prior to Planck's work, classical physics had provided a reliable description of macroscopic phenomena, but struggled to explain the behavior of light and matter at microscopic scales. The quantization of energy presented by Planck allowed for a new way of thinking about the interactions between light and matter, specifically at the atomic level. Planck's work set the stage for other groundbreaking discoveries, including Einstein's work on the photoelectric effect and Bohr's model of the atom. While Planck had focused primarily on radiation, his work laid the foundation for a new way of understanding atomic structure and the behavior of subatomic particles, which would soon become central to the emerging field of quantum mechanics. One of the most crucial aspects of Planck's contribution was his ability to reconcile theory with experiment. Classical physics had failed to explain the behavior of blackbody radiation, and Planck's theory succeeded where others had faltered. His theory was able to explain the observed spectrum of radiation by introducing the idea that energy was quantized and could only be emitted or absorbed in discrete units. Planck's constant provided the means by which this quantization was expressed mathematically, allowing him to accurately predict the results of experiments. This was a major breakthrough in physics, as it demonstrated the power of theoretical physics to solve real-world problems. Planck's approach was not merely an abstract mathematical exercise. It had tangible consequences for our understanding of the natural world. The introduction of the Planck constant also marked a crucial moment in the development of physical constants in science. Prior to Planck's work, the constants of nature, such as the speed of light and the gravitational constant, were known, but their fundamental significance was not fully understood. The Planck constant, however, was a different kind of constant. It was not merely a numerical value used in equations. It was a fundamental feature of the physical world that governed the behavior of energy at the quantum level. The Planck constant became central to quantum mechanics, influencing the way physicists thought about the behavior of particles, energy, and matter. It would later appear in key equations in quantum mechanics, including Heisenberg's uncertainty principle and Schrödinger's wave equation, which would further expand our understanding of the quantum world. In addition to its role in quantum theory, the Planck constant also became a key player in the development of new technologies. The concept of quantized energy and the Planck constant became the foundation for the development of technologies such as semiconductors, lasers, and quantum computers. These technologies rely on the principles of quantum mechanics, which were made possible by Planck's work on quantization. In particular, the understanding of energy quantization has had profound implications for the development of electronics and computing. The principles of quantum mechanics, including the behavior of energy quanta, have enabled the development of devices that have revolutionized modern technology, from computers to telecommunications and beyond. Max Planck's theory of quantized energy was the first step in a long journey toward the development of quantum mechanics. His work laid the groundwork for subsequent advancements in the field, and it set the stage for a radical shift in the way scientists understood the universe. Planck's introduction of the Planck constant and his formulation of energy quantization opened the door to a new understanding of matter and energy at the microscopic scale. His ideas challenged the deterministic worldview of classical physics and paved the way for a new, probabilistic understanding of the physical world. This shift in understanding was not an easy one, and many physicists, including Albert Einstein, Niels Bohr, and others, would build upon Planck's ideas to develop quantum mechanics into the comprehensive theory that it is today. Planck's contribution to science cannot be overstated. His work on blackbody radiation and the introduction of quantized energy were not merely incremental steps in the development of physics. They represented a fundamental shift in how scientists viewed the universe. The concept of energy quanta, though initially introduced to resolve a specific problem in physics, became the foundation for an entirely new field of study. The development of quantum mechanics, driven by the work of Planck and his successors, has transformed not only our understanding of the microscopic world, but also the technological landscape of the 20th and 21st centuries. The implications of Planck's work are still being felt today, as quantum mechanics continues to shape the future of science and technology. The legacy of Planck's work extends beyond the realm of physics. His ideas about quantized energy and the Planck constant have influenced fields as diverse as chemistry, materials, science, and even philosophy. Quantum mechanics, which arose from Planck's early work, has changed the way we think about reality itself. It has challenged our perceptions of determinism, causality, and the nature of existence. The strange and counterintuitive principles of quantum mechanics have led to new questions about the nature of the universe and our place within it. Planck's work has thus had a profound impact not only on the scientific community, but on the way we conceptualize the world around us. Max Planck's discovery of quantized energy was the starting point for a scientific revolution. His work challenged centuries of classical physics and opened the door to a new way of thinking about the physical world. The introduction of the Planck constant and the concept of energy quanta set the stage for the development of quantum mechanics and a new era in physics. The legacy of Planck's work continues to shape the field of physics and other scientific disciplines, as well as the development of new technologies that are transforming the modern world. Max Planck's contributions remain some of the most important in the history of science, and his work continues to inspire new generations of scientists and researchers to explore the mysteries of the quantum world. Max Planck's work on the quantization of energy and the introduction of the Planck constant marked a monumental shift in our understanding of physics. Though Planck himself did not foresee the full extent of his contributions, his theory laid the foundation for the entire quantum revolution that followed. While Planck's primary focus in 1900 was on resolving the problem of blackbody radiation, his findings opened the doors to new ways of thinking about energy, matter, and the universe itself. His work profoundly changed the course of science, and its ramifications can still be seen today in both theoretical and applied physics. The concept of quantized energy, first introduced by Planck, was a direct challenge to classical physics, which had long treated energy as a continuous quantity. Classical physics, based on the work of Isaac Newton and James Clerk Maxwell, had successfully explained many phenomena, but as scientists delved deeper into atomic and subatomic realms, these classical theories began to break down. In particular, the problem of blackbody radiation revealed significant discrepancies between theoretical predictions and experimental results. Classical theory, governed by the laws of electromagnetism, predicted that a blackbody, an object that absorbs all radiation, would emit radiation with infinite energy at high frequencies, an outcome known as the ultraviolet catastrophe. However, experimental data showed that the radiation intensity actually decreased at high frequencies, contrary to the predictions of classical theory. Planck's solution to this dilemma was to propose that energy is not continuous but comes in discrete amounts, or quanta. This idea was revolutionary at the time. Planck postulated that energy could only be emitted or absorbed in fixed quantities, with the size of these quanta determined by the frequency of radiation. This insight came at a time when scientists had little understanding of how energy behaved at the atomic level. Planck's hypothesis was initially a mathematical convenience, a way to explain the observed spectrum of blackbody radiation. However, it became clear that the quantization of energy was not just a mathematical trick, but a fundamental characteristic of the universe. The equation that Planck derived, E equals h nu, where E is the energy of the quantum, h is the Planck constant, and nu is the frequency of radiation, became one of the most important equations in the history of physics. This equation described how energy was related to the frequency of radiation and introduced the concept of a fundamental constant, the Planck constant. The value of the Planck constant, h equals 6.626.07015 times 10 negative 34, text Jace, would go on to play a crucial role in the development of quantum mechanics. The implications of Planck's work were not immediately understood. In fact, Planck himself did not fully grasp the broader significance of his discovery. He saw his theory as a temporary mathematical solution to a specific problem, not as the starting point for a whole new framework of physics. Planck's quantization of energy was viewed as a mathematical tool, a way to make classical theory work in specific cases. He did not initially perceive that his theory would soon lead to a paradigm shift in how scientists viewed the natural world. The first major breakthrough that brought greater attention to Planck's theory came through Albert Einstein's work on the photoelectric effect in 1905. In this seminal paper, Einstein applied Planck's concept of quantized energy to explain the emission of electrons from a metal surface when illuminated by light. Classical wave theory had failed to explain this phenomenon, but Einstein showed that light itself was quantized and that its energy could be described as discrete packets of energy, or photons. Einstein's work confirmed that Planck's hypothesis had real physical implications. It was no longer just a mathematical tool, but a reflection of the way the physical world actually operates at the atomic level. Einstein's explanation of the photoelectric effect won him the Nobel Prize in Physics in 1921 and played a pivotal role in establishing quantum theory as a physical reality. Einstein's extension of Planck's work demonstrated the power of the quantum concept, especially in explaining phenomena that classical theory had failed to address. It was not only light that behaved in discrete quanta, but also other forms of radiation and energy exchanges in atomic systems. Einstein's application of Planck's ideas validated the concept of energy quantization and propelled it to the forefront of modern physics. The photoelectric effect became a key experimental proof that energy quanta were a real, observable aspect of the universe. In addition to Einstein, Niels Bohr's work on the hydrogen atom further illustrated the importance of Planck's theory. Bohr, in 1913, used Planck's idea of quantized energy to explain the discrete spectral lines observed in the hydrogen atom's emission spectrum. Bohr proposed that electrons in an atom could occupy only certain discrete orbits with fixed energy levels. When electrons moved between these energy levels, they emitted or absorbed quanta of energy corresponding to the difference in energy between the levels. Bohr's model was instrumental in explaining the observed atomic spectra and provided experimental support for Planck's quantization hypothesis. The Bohr model, though later refined and superseded by more sophisticated quantum theories, was a significant step forward in our understanding of atomic structure. While Planck's work focused primarily on the quantization of energy, it had far-reaching consequences for other areas of physics, particularly in the realm of quantum mechanics. The development of quantum mechanics, driven by the work of Planck, Einstein, Bohr, and others, fundamentally altered the way scientists viewed the universe. Quantum mechanics is a probabilistic theory, where particles like electrons do not have precise, predictable positions or velocities, as classical mechanics suggested, but instead exist in a state of probability. This was a revolutionary shift in how scientists viewed the behavior of matter at the atomic and subatomic levels. Planck's work also had profound implications for technology. The understanding of energy quantization and the role of the Planck constant led to the development of technologies that are central to modern life. For example, quantum mechanics is the basis for the operation of semiconductors, which are essential components of computers, smartphones, and many other electronic devices. Similarly, quantum mechanics has enabled the development of lasers, which are used in everything from medical treatments to telecommunications. In more recent years, quantum theory has paved the way for emerging technologies like quantum computing, which has the potential to revolutionize fields ranging from cryptography to artificial intelligence. In conclusion, Max Planck's discovery of the quantization of energy and the introduction of the Planck constant marked the beginning of a scientific revolution. While initially intended as a solution to a specific problem in blackbody radiation, Planck's ideas formed the foundation of quantum mechanics, a theory that would profoundly change our understanding of the universe. His work, which was extended by the groundbreaking contributions of Einstein, Bohr, and others, not only solved a critical problem in physics, but also set the stage for the development of technologies that have transformed modern life. Today, Planck's work continues to inspire scientists and researchers as they explore the mysteries of the quantum world. The quantization of energy is one of the most fundamental ideas in physics, and it remains central to the study of the microscopic universe. Planck's contributions to science have left an indelible mark on our understanding of the natural world and have shaped the technological landscape of the 20th and 21st centuries. Max Planck's pioneering work in the early 20th century gave rise to the foundation of quantum theory, reshaping our understanding of energy, matter, and the laws of physics. One of his most significant contributions was his work on the problem of blackbody radiation, which ultimately led him to propose that energy is not continuous, as previously assumed, but is instead quantized. This breakthrough idea would lead to the formation of quantum mechanics, fundamentally altering the way we perceive the universe at both the macroscopic and microscopic levels. The issue of blackbody radiation had plagued scientists for years. Classical physics, specifically the Rayleigh-Jeans law, predicted that an ideal blackbody would radiate infinite energy at shorter wavelengths, an outcome known as the ultraviolet catastrophe. This prediction was in stark contrast with experimental observations, which showed that the radiation intensity fell off at high frequencies. Classical physics could not explain this discrepancy, and it became clear that there was something fundamentally wrong with the prevailing models. Planck's response to this issue was groundbreaking. He proposed a new model where energy could only be emitted or absorbed in discrete amounts, which he referred to as quanta. This idea of energy quantization was a stark departure from the classical view, where energy was considered to be continuous. Planck's introduction of energy quanta marked the first time that a fundamental constant of nature, now known as the Planck constant, was introduced. This constant would later become central to the development of quantum mechanics. Planck used this constant to relate the energy of a quantum to the frequency of radiation, represented by the equation E equals h nu, where E is the energy, EH is the Planck constant, and nu is the frequency of the radiation. This equation not only resolved the issue of blackbody radiation but also introduced a new way of thinking about energy itself. Energy was no longer seen as something continuous, but instead as discrete packets that could only exist in fixed amounts. This discovery would not only provide a solution to the blackbody radiation problem, but would also lay the groundwork for the development of quantum theory, which would later explain the behavior of atoms and subatomic particles. Planck's hypothesis that energy is quantized opened the door to the idea that the laws of physics at the atomic and subatomic levels are fundamentally different from those that govern larger-scale systems. This insight was pivotal in the shift from classical to quantum mechanics. It was a shift from a deterministic worldview to a probabilistic one, where the behavior of particles could not be precisely predicted, only understood in terms of probabilities. While Planck's quantization of energy was initially a mathematical tool to explain a specific problem, its deeper significance was not immediately recognized. Planck himself viewed his hypothesis as a temporary fix, a mathematical device to make the theory of radiation fit experimental data. However, as other physicists began to explore the implications of Planck's work, it became clear that his quantum hypothesis was a revolutionary concept. The quantization of energy would later become a cornerstone of quantum mechanics, influencing the work of other physicists such as Albert Einstein, Niels Bohr, and Werner Heisenberg. Einstein's work on the photoelectric effect, for instance, extended Planck's ideas to explain the nature of light as both a particle and a wave, thus solidifying the concept of energy quanta as a fundamental feature of nature. Bohr's atomic model and Heisenberg's uncertainty principle further built on Planck's work, culminating in the development of quantum mechanics as a full-fledged theory. The idea of energy quantization fundamentally altered our understanding of the physical world. It introduced a new framework for explaining the behavior of matter and energy at the atomic and subatomic levels. Classical physics, which had served humanity well in explaining the behavior of large objects and systems, was inadequate at explaining the phenomena that occur at the microscopic scale. Quantum mechanics, built upon Planck's insight into the quantization of energy, provided the tools to understand the behavior of electrons, atoms, and molecules. It laid the foundation for technologies that would transform the world, such as semiconductors, lasers, and eventually quantum computers. Max Planck's work on blackbody radiation and his introduction of the quantization of energy were seminal moments in the history of physics. His insights opened up new areas of exploration in physics, challenging long-held assumptions and leading to the creation of quantum mechanics. Today, quantum theory not only governs the world of subatomic particles, but has also revolutionized various fields of science and technology. From the devices that power our computers to the new frontiers of quantum computing, Planck's legacy continues to shape the future of science. His work exemplifies how a single idea, born out of necessity to solve a specific problem, can change the course of human knowledge and innovation. Max Planck's contribution to the understanding of the quantum world began with his attempt to solve the long-standing problem of blackbody radiation, which had confounded physicists for decades. Blackbody radiation refers to the electromagnetic radiation emitted by an object that absorbs all incoming radiation, and it was the subject of much debate due to discrepancies between theoretical predictions and experimental observations. Classical physics, especially the Rayleigh-Jeans law, predicted that the radiation intensity would increase without bound as the frequency of radiation increased, resulting in an infinite amount of energy being radiated at shorter wavelengths, which became known as the ultraviolet catastrophe. However, experimental data showed that this was not the case. Instead, radiation intensity decreased at high frequencies, prompting the need for a new approach to explain this behavior. Planck's solution to this problem was a revolutionary idea. He proposed that energy is not emitted or absorbed continuously, but in discrete amounts, or quanta. This was a dramatic departure from the classical notion that energy could be varied continuously, like a flowing stream. Planck's hypothesis stated that the energy of oscillators within the walls of the blackbody could only take certain discrete values, depending on their frequency. These discrete energy levels were determined by the formula E equals h-nu, where E is the energy of a quantum, h-nu is Planck's constant, and nu is the frequency of radiation. This was the first instance in physics where the concept of quantization energy coming in discrete packets was introduced, forever changing the trajectory of scientific thought. The significance of Planck's theory extended beyond its immediate application to blackbody radiation. While his primary goal was to resolve a specific experimental discrepancy, the broader implications of his work began to emerge. Planck's quantization of energy laid the groundwork for quantum mechanics, a theory that would later be developed by physicists such as Albert Einstein, Niels Bohr, and Werner Heisenberg. These scientists would extend Planck's ideas, leading to the creation of a comprehensive framework to describe the behavior of particles at the atomic and subatomic levels. Planck's idea that energy levels were quantized rather than continuous turned out to be a central concept that underpins the entire field of quantum mechanics. This change in perspective opened new doors for understanding atomic structure, molecular interactions, and the fundamental nature of matter itself. Although Planck's contribution was revolutionary, his own perception of it was more cautious. Planck did not initially view the quantization of energy as a fundamental aspect of nature, but rather as a mathematical convenience, a tool to make the theoretical predictions match experimental results. He saw his work as a temporary solution to the problem of blackbody radiation, not realizing that his ideas would set the stage for an entire field of study. However, as the scientific community began to recognize the power of the quantum concept, it became clear that Planck's hypothesis was far more significant than he had anticipated. The realization that energy levels are quantized would become a cornerstone of quantum theory, radically altering how physicists understood the universe. Planck's introduction of the Planck constant, symbolized by h, also played a pivotal role in the development of quantum theory. The constant defined the scale at which quantum effects become significant, and it became one of the fundamental constants of nature. The Planck constant would appear in nearly all subsequent formulations of quantum mechanics, and it provided a bridge between classical physics and the new quantum world. In addition to its theoretical importance, Planck's constant also had practical consequences in fields such as semiconductor technology, where it governs the behavior of electrons in materials. The influence of the Planck constant can be seen in modern technologies such as lasers, atomic clocks, and even the functioning of computers, where the principles of quantum mechanics, rooted in Planck's initial discoveries, are essential. In summary, Max Planck's introduction of the concept of quantized energy not only solved a specific problem in blackbody radiation, but also sparked the development of quantum mechanics, a theory that has since become the foundation for much of modern physics. His idea that energy is discrete, rather than continuous, was the key to unlocking the behavior of matter at the atomic and subatomic levels. The introduction of the Planck constant, which provided a way to measure the size of these energy quanta, further cemented his contribution to science. Although Planck initially viewed his discovery as a mathematical tool, it ultimately led to a profound transformation in our understanding of the physical world. His legacy lives on, as quantum mechanics continues to influence a wide range of scientific fields and technologies, shaping everything from computing to the exploration of the universe. Max Planck's groundbreaking work in physics is best known for introducing the concept of energy quantization, which laid the foundation for quantum mechanics. His work started with the problem of blackbody radiation, an issue that had puzzled physicists for decades. Classical physics, particularly the Rayleigh-Jeans law, predicted that an ideal blackbody would radiate infinite energy at short wavelengths, which led to the ultraviolet catastrophe. However, experimental data showed that the radiation intensity decreased at shorter wavelengths. This discrepancy between theory and experiment led Planck to propose a radical new idea. Energy is not emitted or absorbed continuously, but in discrete units or quanta. Planck's hypothesis was initially introduced as a mathematical solution to the problem of blackbody radiation. He proposed that energy could only be exchanged in specific amounts, proportional to the frequency of the radiation. This was a radical departure from classical ideas, where energy had been viewed as continuous. Planck's formulation, E equals h dot nu, where E is the energy, h dot is the Planck constant, and dot nu is the frequency of radiation, suggested that energy is quantized. Though initially seen as a mathematical trick, Planck's idea of discrete energy levels would turn out to be the cornerstone of a new way of thinking about energy and matter. Planck's work not only resolved the issue of blackbody radiation, but also marked the first step toward the creation of quantum theory. The introduction of quantized energy fundamentally changed how scientists viewed the microscopic world. Prior to this, classical mechanics had been able to explain the behavior of large-scale systems, but it faltered when it came to explaining the interactions at the atomic and subatomic levels. Planck's discovery signaled the end of the classical era and the beginning of a new scientific framework. His ideas about quantized energy laid the foundation for future developments in quantum mechanics, a theory that would explain atomic behavior and lead to technologies that transformed the modern world. Although Planck himself was initially cautious about the full implications of his work, his discovery became the stepping stone for many other physicists, including Albert Einstein, Niels Bohr, and Werner Heisenberg. Einstein extended Planck's concept of energy quanta in his explanation of the photoelectric effect, which showed that light behaves as both a particle and a wave. This provided crucial experimental evidence for Planck's hypothesis and further validated the concept of energy quantization. Bohr used Planck's quantization of energy to explain the structure of the hydrogen atom, offering a new model of atomic behavior that would shape the course of future atomic theory. One of the most significant contributions of Planck's work was the introduction of the Planck constant, a fundamental physical constant that defines the scale of quantization. The Planck constant, h equals 6.62607015 times 10 negative 34, text Jace, became central to quantum mechanics and appeared in many of the foundational equations of quantum theory. Its role in relating the frequency of radiation to the energy of quanta established a new way of looking at the fundamental nature of the universe. The Planck constant also plays an essential role in technologies that rely on quantum mechanics, including semiconductors and quantum computers. Planck's ideas, though initially met with skepticism, ultimately led to the birth of quantum mechanics, which has since become one of the most successful and widely used theories in physics. Quantum mechanics has provided an accurate description of the behavior of particles at the atomic and subatomic levels and has driven the development of technologies that have revolutionized the world, from lasers to transistors and beyond. Planck's legacy continues to influence scientific research and technological innovation, and his work remains a cornerstone of modern physics. Max Planck's work in the early 20th century is considered a cornerstone of modern physics, especially for his role in the development of quantum theory. His groundbreaking idea arose from his efforts to resolve a major issue in physics at the time, the problem of blackbody radiation. Blackbody radiation refers to the electromagnetic radiation emitted by a perfectly black object that absorbs all incident light. Classical physics, based on Rayleigh-Jean's law, predicted that this radiation would increase infinitely at short wavelengths, but experimental data clearly showed that radiation intensity decreased as wavelengths shortened. This discrepancy, known as the ultraviolet catastrophe, was a fundamental flaw in classical theories that Planck sought to resolve. Planck proposed that energy is not continuous, as classical physics had assumed, but rather is emitted or absorbed in discrete amounts, or quanta. This hypothesis marked the birth of quantum theory. According to Planck's idea, energy could only exist in fixed amounts proportional to the frequency of radiation, represented by the equation E equals h nu, where E is the energy, is the Planck constant, and nu is the frequency of radiation. This was a revolutionary departure from the classical view of energy as a smooth and continuous flow. The significance of Planck's work was far-reaching. His concept of quantization of energy was initially intended to resolve the issue of blackbody radiation, but its implications went well beyond that. Planck's introduction of quantized energy levels set the stage for the development of quantum mechanics, a theory that would explain the behavior of particles at atomic and subatomic scales. This idea of energy being quantized would become a cornerstone of quantum mechanics and would lead to new ways of understanding the microscopic world. While classical mechanics had been effective in explaining large-scale phenomena, it failed at the atomic and subatomic levels. Planck's work provided a new framework to understand these phenomena. Although Planck himself viewed his theory as a mathematical tool to solve the blackbody radiation problem, the deeper implications of his work became clearer with time. Planck's discovery provided the foundation for future developments in quantum theory, including Albert Einstein's explanation of the photoelectric effect in 1905. Einstein used Planck's concept of energy quanta to explain how light, when shined on a metal surface, could cause the emission of electrons. This was an important step in confirming that light behaves both as a wave and as a particle, and it validated the notion of energy quantization. The introduction of the Planck constant was another monumental step in the advancement of physics. This fundamental constant, denoted as HA, is key in determining the size of the energy quanta. It would later become one of the most important constants in quantum mechanics, appearing in equations that describe the behavior of particles, including Heisenberg's uncertainty principle and Schrödinger's wave mechanics. The Planck constant's significance extended beyond theoretical physics and was also pivotal in the development of technologies that rely on quantum mechanics, such as semiconductors and lasers. Planck's contributions were not immediately fully appreciated. Initially, his ideas were met with skepticism as they radically departed from classical physics. However, over time, as further research built upon Planck's work, his theories gained acceptance. His concept of quantized energy laid the groundwork for the eventual development of quantum mechanics, which became the dominant theory in physics by the mid-20th century. This new theory not only revolutionized our understanding of the microscopic world, but also had profound technological applications, leading to innovations that are integral to modern life. Max Planck's legacy remains profound. His insights into the quantization of energy paved the way for the exploration of the atomic and subatomic realms, fundamentally changing the landscape of physics. His work laid the foundation for quantum mechanics, which continues to be a driving force behind scientific research and technological advancements, from the development of quantum computers to innovations in communication and energy technologies. Planck's ideas still shape our understanding of the universe, proving that even a simple, seemingly mathematical solution can have far-reaching effects on how we perceive the world around us.